Since this is the last talk by a non-organizer, maybe I should take the opportunity to say thank you to all the organizers, not just of this workshop here, and for inviting me here, but for this putting together this whole program, which is coming to an end today. I think a program like the one we had here is an ideal combination of having exciting times like this week or so, where everybody gets together for a workshop, but also the necessary calmer times which we need to do in mathematics, to work with collaborators, or maybe just to think. So in this sense, I can only hope that all of us keep this in mind and look for such opportunities in the future, and if there are such opportunities, also make the effort to apply for them and organize them. So I think this is very important to keep our research in our field going. So thanks to Lonya, Frederick, Daniel, Lana, and David, Lana and Sasha. So I want to, before I get to any concrete results, I want to spend the first part of my talk by talking about a question which has been asked quite frequently recently, in particular by physicists. So there is, I think, no universally agreed upon answer yet to it. So it seems to be still somewhat controversial. So what you're seeing will be my take on it, which might also be time dependent, and change over time. But I think there is a little bit of convergence visible now, so to some of the concepts which should be involved in this topic of many-body localization. So just one slide before I can try to distinguish many-body localization. So the easiest possible case of one-body localization, just to remind everybody what we have seen it many times this week. So if I just stick with the standard classical Anderson model, and for the sake of this lecture, all I will need is the one-dimensional version. So we have come to think of this as sort of the quantum mechanical model of a single electron, quote unquote. This is already discretized, whatever that is. Maybe it's really a tight binding Hamiltonian in a disordered background. So which I keep 1D. So then I have the discrete hopping operator here, and the potential nu n, whose values are given by IID random variables, and I will always assume that they're sufficiently smooth in their distribution, so probably bounded, compactly supported density. These are the assumptions under which the following result on one-body localization is known. Already in one particle localization, there are various ways in which we have all described localization, spectral, dynamical, statistical. We know a lot about the equivalences between these different ways of saying things, but that should already make us suspicious about many bodies. So there obviously will also be many ways of saying these things and understanding how they are related. And I want to talk about some of them, which might not be the final picture. So what I have put here is what would now be called eigencorrelated localization, so which particularly includes dynamical localization. So here is the Anderson model. Here you take any function of the self-adjoint operator in the sense of the functional calculus and look at the matrix elements j, k. And here's the interesting thing. You can actually take the supremum over all Borel functions or whatever, which are pointwise bounded by 1 in modulus. So this in particular, of course, includes the case of dynamic localization, where you just look at the function gtx equal e to the minus itx. So then g of a just gives you the dynamics, and what I'm looking here is sort of the transport kernel, so I could say. And then I could just replace the sup over all g by a subset, just taking the supremum over all times t. So that statement is included there. But somewhat actually important for some of my talks that other functions can go here. So then I think eigencorrelator localization is the word. And okay, and I will assume exponential decay here, that one can get that for smooth enough distributions, but there are versions of what I have to say which work for sufficiently strong power decay or stretched exponential decay, but just to stay specific. So now, how to move on to many-body localization. So Anderson acknowledges this already in his very first paper in 1958, so that he thinks of his model as somehow the most simple, non-trivial model of trying to just say something about diffusion and quantum diffusion, which he has clearly been thinking of as a many-body phenomenon. And he's aware of the fact that basically what he does with that model is neglecting interactions between the electrons. So that is essentially the main question. So how, what can one say about interactions? So what is so when we go beyond the Anderson model, the most important thing from the physical point of view to understand, if you say look at a many-body electron gas, what is the effect of interactions? And this is already the first time I want to stress many-body here, an electron gas. So when I say many-body, I mean not 3 or 17. I mean more like 10 to the 23 or maybe infinity. So when it comes to localization, the question is, does the many-body system stay localized? You still embed all this many-body system in this disordered, fixed, quenched background, but you add the interactions. So we know, at least if we start with a 1D system, that the non-interacting system is localized, or the one particles are localized. If we switch on, say, if you have small interaction strengths, or maybe low electron density, typically they are far away from each other, so the interaction is already very weak at that distance. Can we hope that a localization phenomenon survives? And I must say, it comes as somewhat of a surprise to me that even in physics, it seems this question was very much neglected for almost 50 years. So that people were happy with the Anderson model, and only much more recently this field became very active. So where you say it's not just the Anderson model, where you want to say something about interactions. So I think this recent surge of activity was strongly motivated by another direction, by actually coming from quantum information theory, where, well, when people try to build a quantum computer, they also look at interacting quantum systems and transport between them. So there has been a flood of papers in the theoretical physics literature and in the quantum information literature over the last decade. So a lot is going on right now, and this in particular discussion of what many-body localization should be, I think, has only recently been really popularized. So what then is many-body localization? So maybe start with the first and rather rough attempt at an answer, where I want to stress that one should think differently of a one-particle system and a non-interacting many-particle system, even if the mathematics is basically the same. But physically it means different things. In particular, once you perturb, you have to think of them differently. So what is, in a way, trivial is a non-interacting many-body system. What is that? This means the n-body system, the Hamiltonian of the n-body system, is just the sum of the Hamiltonians of the one-particle system. And this acts on the many-body Hilbert space, which is the tensor product of the one-particle Hilbert spaces. And again, I want n to be, think of n as rather large. So maybe the best is to read this backwards here. So if little h is the one-particle Hamiltonian, and little h sub j will always indicate a local Hamiltonian acting on the jth side of a tensor product. Everything else is identities. So this is what I have here, and that I sum up over J. So that would be the Hamiltonian of a non-interacting many-body system. I don't care about Fermi or boson statistics, so I look at the full tensor product for these matters here. And okay, mathematically, once you can handle the one-particle system, it's sort of trivial to handle the many-particle system, non-interacting many-particle system. So the eigenstates of the many-particle or the non-interacting many-body system are just the product states of eigenstates of each one-particle system. For this, I could even have different h's at each side if I wanted to. And the dynamics of the many-body system is just a tensor product of the dynamics of the single particles. So they all move for themselves, but then you tensor them together. So, and then I said here at the top, to call an interacting many-body system many-body localized, one attempt at defining this or at going about it would be to say, okay, I want to show that the system has properties whichever similar to a non-interacting many-body system. And, this I will try to make a bit more precise for the rest of the talk, and actually already on the next several slides. So on this slide and on the next one, I have a list of more concrete examples of such properties which people have started using, so it seem to be relatively well accepted as having to be part of the many-body localization regime. If they fully characterize it is a different question, but that you should be able to show that for a concrete system where you suspect that it's many-body localized. So these first two criteria here are versions of what I said about the eigenstates of the non-interacting system are products of one-particle eigenstates. So I would like a many-body localized many-body system to have eigenstates in some sense close to product states. And this is what these two items are saying. So a very classical thing in theoretical physics is to measure closeness to product states is of course correlations. So if you have product states have no local correlations, if you let two local operators act on them, which act at different sides, there are no correlations. If you can then show that for sufficiently far sides the correlations are exponentially decaying, that would be in some sense closeness, one indication of closeness to a product state. And that is something so you can immediately, physically speaking, look at in three different situations, physically corresponding to different temperatures. So you can just start with studying correlations of the ground state of a many-body system, see if you can prove exponential decay. But here I would like to stress that if you really want to consider this already just the ground state alone, proving exponential decay, if you want to consider this an indication of many-body localization, you should look at systems which don't have a ground state gap. If you have a ground state gap, then exponential decay of correlations is something like the many-body analog of a Cope-Thomas bound, so of exponential decay of an eigenfunction for an eigenvalue below the essential spectrum. This is not mathematically equivalent, but this is sort of how I think of it. So you would rather not have a ground state gap, or at least not a uniform ground state gap in the volume of a system, and still be able to show exponential decay of correlations. Physically looking at positive temperature systems would mean to look at the same question for thermal states, which are now not pure states, standard Gibbs thermal states, or the infinite temperature limit, which would actually say you want to say something about correlations or the exponential decay for arbitrary excited states in the system, which maybe looks rather unlikely, because you would also want to include very high energy in that. So much about correlation decay as one way of measuring it. I want to spend more of my actual time today about another way of measuring closeness of states to product states, namely entanglement entropies and so-called area laws as an indicator of being close area loss for the bipartite entanglement as an indication for being close to a product state. So I'll define all that a little bit later. Again, you can ask this for ground state, excited states, thermal states. Before I move on with any specifics, here are a few more items. So this was about eigenstates. Sort of, in a way, the closest analog you can think of in the many-body case of spectral localization. You don't really want to use spectral characteristic in a many-body case. First of all, because I work in finite volume, I will always work in finite volume, so everything is discrete. But properties of the eigenfunctions, that is sort of the closest thing I can imagine to what in the one-body case we call spectral localization. Let's look at dynamics. So a dynamic localization for a one-particle system is no transport. And so here I would say, in analogy, no many-body transport. And here I'm saying in the form of a zero-velocity Lieb-Robinson bound. It will not be my main topic today, but I will show at least one slide. But let me draw a picture here just to get my point across. So what I mean by no many-body transport. So if this is the configuration space of one particle, Z, or R, so I said a single electron. So then localization of this electron means it doesn't move in the vertical direction in time. So how do I turn this into a many-body system? Well, let me produce a many-body quantum system, a many-body lattice system. Sort of a baby version of a discretized quantum field, so maybe. But I want this to be many lines, so n very large. So that would be a non-interacting many-body system. And each electron, say, also could be localized in its configuration space or not. And now I want to introduce an interaction. And this is very symbolically here, so I'm not writing anything down. So there is interaction maybe between next neighbors in this system. Of course, you could do more complicated things. And so here is, when it comes to dynamics, so one-body localization, let's cross this out, would be the suppression of any movement along one of these, a vertical line. That's one-body localization. Many-body localization, I think, should refer to the horizontal axis. So many-body localization means there is no transport along the horizontal axis, and that is, of course, not particle transport at all, because all these particles are glued to their sites. What this is, if anything, is information transport between these particles. So I think this is what these Lieb-Robinson bound have turned out to be measuring. They're also much older than the interest in quantum information. They're from the early 70s, but they really had a big rebirth over the last decade, because they seem to be a tool to do exactly that. That will actually be my first result, which I show, because it's actually the first one we started with in some very simple models. If I have time, I will show something about growth of dynamical entanglement. That's a situation where I have a product state at time 0 and then look at the dynamics of an interacting Hamiltonian and ask, will it get entangled over time? And the one thing which crystallizes more and more out of the literature and probably got the whole new wave of interest started by two papers, Gorny et al. 2005, Basco et al. 2006, is the question of Fock space localization. So this might very well be where all this is going, or what all of this is following from, if one finally nails it down. And this is, of all, I think the only serious attempt at getting to this is by John Embry, his paper from last year, I think, to directly get at this point, and then maybe everything else should fall out. But I'm not at the point where I feel I can say something useful about this. So I will stay with these other more specific characterizations. And I will also stay with very simple models, so that might be appropriate for a talk on the last day of the workshop. But that is certainly not the ultimate goal. So the best available models for rigorous work so far, because one can actually really more or less go through and one by one check these things which I have been listing, is disordered harmonic oscillator systems. So here you can really think of each of the vertical lines as a one-dimensional harmonic oscillator, and this as an extra spring connecting the two, and write down the quantum equations for that. And we learn in quantum mechanics 1 that we can write down Hermite functions, blah blah blah, and solve all this explicitly. So these are two papers which we looked at in 2012 and 2013. And then the model I will mostly focus on, or actually exclusively focus on today, is the XY spin chain in random field, where one also has now a pretty complete picture. So this slide also serves to list all my co-authors on this. So we have Bruno Nachtergaane from UC Davis, Bob Sims from Arizona, Eman Hamza from Cairo, Bob again, and Hussam Abdul Rahman, current PhD student of mine. And Simone Watzel is not really a direct collaborator because she's doing related work with Bob Sims, but she's also on here. And that is not yet out, so but Bob keeps telling me what they're doing. So and I have every reason in the world to say that these are simple toy models and not the ultimate goals. Why? Because both of them can be reduced to the study of an effective one-particle Hamiltonian, not just heuristically or approximately, but completely rigorously. And everything about this one-particle Hamiltonian implies pretty much completely. If I know the one-body Hamiltonian, I know the many-body Hamiltonian. So, and so this is these are the kind of results I want to explain. So, and I will stay with the XY chain in random field. I somehow like to start immediately by introducing the anisotropic version, because that is actually physically and mathematically quite interesting. Although I will, for today, for the sake of simplicity and time, mostly stick with results for the isotropic case. So, but let's go slowly. One major simplification, which I do here, I take my particles to be spins. So if every single particle here is an electron, that means that the single particle Hilbert space is already infinite dimensional, and then I want to take a large tensor product of already infinite dimensional one-dimensional basis. That's certainly what you would want to do to study an electron gas, but it's seemingly quite hard. So what I do by replacing the electrons by spins, also going under the name of qubits, is to replace choose the one particle Hilbert space simply as C2, finite dimensional, two-dimensional Hilbert space. So here's just a C2 sitting. So that actually completely eliminates one particle transport. There is no transport on two sides. So at least there's nothing interesting to say about it. And so it means I have a model where I can completely focus on, say, the new thing, on the horizontal line, what happens between these particles. And for the quantum information people, that is, of course, also the exchange of information between qubits in, I don't know, the quantum computer they want to build one day or something. So now you have to put a Hamiltonian on the many-body space. And if you wish, I could maybe read it backwards. There is first a local part. This is just a sum of local Hamiltonians given by the Z Pauli matrix acting on the jth side of these n sides and multiplied by a random coefficient, nu j. So that would be just a non-interacting system. But then I add next neighbor interactions. So you see here the first side interacts with the second one through these two terms, and that goes all the way to n minus 1 interacting with the nth one. I choose what the people call open boundary conditions. I don't put it on a circle, so n does not go back to 1 for a good reason, actually. So this is, in some sense, simplified version of the full Heisenberg model, where you would also have a third interaction term. with the product of the Z Pauli matrices, but in another sense it's actually a bit generalized because it's an anisotropic version, as I said. So this gamma mostly serves to measure the possibility to choose a different strength for this interaction than for this. So gamma equals 0 would be the isotropic case, which I will mostly look at. So, and again, for the new J's, I will make the same assumption as for my Anderson model earlier. So I think by starting from an infinite array, 1 to infinity of IID random variables with sufficiently regular distribution, which I choose for my exterior fields. So, okay, so that has been known for more than 50 years in physics, that this can be reduced to a one-particle Hamiltonian. So this is the famous paper by Lieb, Schultz, Modis, I think the most cited paper of Elliott Lieb ever, at least if you include the physics literature. So this transformation is older, named after Jordan and Wigner, but I think it's really this Lieb, Schultz, Modis paper which realized that one can use this to show that the XY model is an exactly solvable many-body system. So what do? You introduce actually a system of fermionic creation and annihilation operators, characterized by satisfying the CAR listed here. And how do you get them? You get them by this J is 1 by starting at the left end of the spin chain, the first side, taking the Z Pauli matrix and multiplying all of the Z Pauli matrix up to J minus 1. And then the last factor is AJ. This is just the local lowering operator that would move the upspin to a downspin here. And then it's just simple algebra to check that this is a fermionic system, satisfies the CAR, and a bit more algebra actually shows that Hn can be written as a quadratic Hamiltonian in this fermionic system, and that always makes the physicists very happy, and should also make the mathematicians very happy, because this is really now exactly solvable, assuming that you can diagonalize the matrix Mn. So C is just my short way of putting all these creation and annihilation operators into a long column vector, so I don't have to write the usual double sums you see in the physics papers here. Call it Einstein notation or whatever. But and the Mn just collects all the coefficients which appear here, and if you do that, you see the following. Mn actually becomes a 2n by 2n matrix because I have both sets in here. So it has block structure an, bn minus an. That particular block structure immediately means it's unitarily equivalent to its own negative. So spectrum in particular is symmetric to 0. And what do I have for my diagonal and off-diagonal blocks? The diagonal block is just the Anderson model, or minus the Anderson model. So or a finite interval version of it, of the Anderson model, hopping 1 and IID random variables in the diagonal. So here you have the Anderson model, and here you have the negative Anderson model. And in the isotropic case of the XY chain, so that's characterized by gamma equals 0. The Bn is just the 0 matrix. So in the isotropic case, if my effective one-particle Hamiltonian is basically just the Anderson model and plus a direct sum of its own negative, which means all I have to understand is the Anderson model in order to An in order to understand Hn. If I have gamma non-zero, it becomes mathematically a bit more interesting, and there has been some work going on over the last half decade over these block random operators, because there was some work necessary to extend the methods which we all knew for more standard monotone cases. It's non-monotone in the random parameters because of this An minus n. It was one of the challenges. So this is the reduction to the effective Hamiltonian. So now I still would have to, that doesn't mean that I'm immediately done. So I now want to show you results which are of the type, if I know a localization property of Mn, does that give me a localization property of Hn? And that should then better be a many-body localization property. So this is, so Mn is a little bit drowned out by all the noise. Yeah, the A and the Bn got way too big so that you don't see the Mn. So Mn just contains these A's as blocks. This is the Mn. So again, in the isotropic case, the Mn is really just the Anderson model. Because the Bn is not here, and it's decomposed into a direct sum. So that's what you can keep in mind. So I'll try to be relatively brief about my first two slides and just showing you some results, because I really want to get to this entanglement stuff, which is the newer stuff, the newer results. So it's always what one wants to talk about. So this is actually the first thing we found. Started working on this with MN and Bob, is a result on relating dynamical localization of the one particle Hamiltonian to many-body dynamical localization as measured by Lieb-Robinson bounds for the many-body Hamiltonian. And it's really an if-then statement. So if Mn is dynamically one particle localized, in the sense of my very first slide was the brief review of the Anderson model. So that means there is a positive decay rate and a finite constant c, such that the average of the supremum over time of the time evolution kernels has matrix elements decaying exponentially in j minus k. So as I said, that is actually a special case of this eigencorrelated localization. So, but it's, yeah.
Mn is already many body Hamiltonian, and you incorrect one particle localized. What does it mean?
So let me go back. So I don't think Mn is a many-body Hamiltonian, because this is really, you see, something major happened here. I actually reduced the study of an operator in a very high dimensional Hilbert space. This is an operator in a 2 to the n dimensional Hilbert space. That's sort of characteristic, you know, from the tensor products and the many-body, to an operator in a just 2n by 2n Hilbert space. But of course, one slight thing happened. So I think, particularly if the BNs are not here, this is just our most favorite one-body random Hamiltonian, the AN, in an n-dimensional Hilbert space. But the one thing which happened is that this one particle in the one particle operator is not the same particle as the individual particles in the original spin chain. We started with spins, and we end up with a single electron. So in this, yeah, so this happens. It's not like I can explain the properties of a spin chain by just understanding a single spin. That's not what I'm saying. So what comes out is actually an electron, and I think Anderson was fully aware of these connections of spin systems. So if you look at the one particle subspace or the one exciton regime of a spin system, that this was one of the motivations for his model, for writing down his model. Yeah. So that is what we know for the Anderson model, and by now also for a large class of these random block operators, by work of people in the room, I think. But then we get many-body localization for Hn, and we measure this by a zero velocity Lieb-Robinson bound. Again, we need disorder averaging both of these results. So let's look at the formula. So what I have here is one of these so-called Lieb-Robinson commutators. I take a local observable. So I just take a 2 by 2 matrix. That's an operator acting on a single spin, state in C2. I let it act on the jth spin in the chain. And then if I, for the moment, look at time equals 0, the time evolution is just the identity. So I'm just commuting AJ with BK, and BK is another local Hamiltonian given by a 2 by 2 matrix acting on the kth side. And of course, as long as these are completely local, they commute. For time equals 0, if J is not K, they commute. So this is just 0. The whole left-hand side is 0 for time 0. But as soon as I have positive time, and then larger and larger times, this, due to the interaction terms in the spin chain, this will become a non-local Hamiltonian. This will not just act on the jth spin. In fact, quantum mechanics basically tells us that it will immediately act on all of them. But we use the smallness of this commutator as a measure on how much this Heisenberg evolution of this local observable AJ interacts with the local observable at the kth side. And we get exponential decay in J minus K once again. So it's completely clear that this is homogeneous in the norm of A and B, so these two factors must appear here. But important is I take the supremum over T, so this stays exponentially small in J minus K uniformly in time. And the constants C prime and mu prime are also completely independent in the size of the many-body system, in the length of the spin chain. That's also important. So I work in the finite volume regime for these many-body systems simply because I don't want to bother with infinite tensor products. Then I would have to work with C-star algebras and so on. So I want to keep my Hilbert space because I'm used to that for my whole career. So I work with spin chains of length n because I still have a Hilbert space, but then what I have to do in order to make it physically relevant in the many-body regime is to prove results where the constant do not depend on the system size.
If you turn off the magnetic field, what do you get when you do the calculation?
You get ballistic transport. The more classical Lieb-Robinson bound, of course, has a velocity in it. So in the more classical Lieb-Robinson bound, instead of this purely exponentially decaying term, you have to subtract something of the form Vt with a positive V. Which actually means that this is a useful bound only up to certain t's proportional to j minus k over v, and then is interpreted actually as v giving the group velocity in the system. If there is a velocity that is ballistic many-body transport. Now, for that, of course, if you really want to prove ballistic transport, you have to talk about lower bounds too. And that actually for a long time was only sort of implicitly in the old Lieb et al. Papers or in Bratelli-Robinson. But just recently, David Darmonic, Milivoje Lukic, and William Jessen got together and wrote that down for the general periodic case. If you have a periodic magnetic field, actually, you will have a positive many-body velocity in this system. So that actually also inspired some new one-particle questions, so in order for them to prove that. So, okay, I have to move on a bit. Now very quickly about, maybe I should skip this altogether. Yeah, let me skip this altogether. So this was a slide about correlations. So I said I have two different ways of trying to describe that. Eigenstates or of the many-body system could be close to eigenstates of a free non-interacting system, meaning close to product states. Correlations is one of them, but let me talk about the newer one, namely entanglement. And for this, since this is not something which maybe other than Alex Sobolev in the very first talk this week, otherwise such things were not mentioned this week. Let me go through the definitions somewhat carefully. So I start with my chain of length n, and I take an arbitrary subchain of length L. And that can either be a left end of the chain, but it actually doesn't matter. It can start anywhere at an R and end, I guess it has to be R plus L minus 1, so that this subchain has length L, and then I want to know how eigenstates on the whole system are entangled with respect to this subsystem. So how do I measure this? So this splitting of a system into a subsystem and its complement gives me a bipartite decomposition of the many-body Hilbert space. The first factor just coming from all the components in the tensor product corresponding to the subchain, and the second factor to these two pieces at the left and right, which are outside the subchain. Maybe you really want to think of left and right ends, so then these are just the left and right ends. So I start with a pure state in the many-body Hilbert space. So a pure state that just means an element in the Hilbert space of norm 1, and I denote rho phi as the corresponding rank 1 projection. And now I want to take partial traces. So this is the first step to measure entanglement entropy. So I trace out the external degrees of freedom. I take the partial trace over HB, the complement of the subsystem, in this rank 1 projection. what I get is still a state, but a mixed state. So in the sense of a positive trace 1 operator, but it's not pure anymore. So this is now a state on just the Hilbert space HA, but it's mixed. And how mixed it is something which we know can be measured with the von Neumann entropy. The von Neumann entropy of a state in a Hilbert space, of a general mixed state in a Hilbert space, is 0 if and only if it's a pure state. So I want to measure how mixed that gets, and this is just the von Neumann entropy of that state now. So if the original rho phi would have been a product state, then after tracing out the exterior degrees of freedom, I'm just left with the first factor, which is still a pure state, and I would get entanglement 0. But as long as my phi is not a product state, I will get a mixed state and I will get positive entanglement. So this is sort of the basic reasoning why this is a measure of how far away the initial state is from a product state. And that was what I said at the beginning. That is one way one can try to think of many-body localization. I want to apply this to eigenstates now of the system. And I want to find a measure how close they are to product states. That would mean the many-body system behaves in that sense as if the non-interactions were not there. And here's our result on that. So this was actually proven while I was here. So of course, Osam was not here, so that was done by email, but really all this quiet thinking, which I had here, also helped a lot with that. If I know that the many-body Hamiltonian is almost surely simple, that's an important condition, but we can verify that for the spin system, also looking at the Jordan-Wigner transform. And it's important for that we work in finite volume. Then I can start with analytic perturbation theory and do that. It's not hard. And if the one particle Hamiltonian has localized eigenfunction eigencorrelators. So this is actually the definition I started from, or the left-hand side I started from in the definition of localization of eigenfunction correlators. But that's even a weaker version here. At the beginning I said in the concrete models we know, particularly the Anderson model, we know this even with exponential decay. Okay, we analyze our proof and all we need is sufficiently fast power decay. Actually beta equal 2 will already do. So that is well known for many of the examples of the effective Hamiltonian here. Then I get a uniform area law for the entanglement entropy of all the eigenstates of the many-body system. So that I need to explain a bit more, and what I mean by this. So here is the entanglement entropy of an eigenstate. So I just said this being non-zero is a measure of rho phi not being a product state. But I want it to be not too far from a product state. So, and therefore I want upper bounds on the entanglement in order to say that is an indication of many-body localization. So proving that a whole family of entropies of eigenfunctions has a uniform upper bound has this meaning. So here I take the soup over all normalized eigenstates of the many-body system. So this goes way beyond the ground state. I can look at very high energy states of this system and still can include that in the uniform bound. Again, after averaging, but also very importantly, uniform in the size of the original system and also uniform in the size of the subsystem L. And that's the other important thing here. Uniform in the size of the subsystem, because that is something which can generally grow. Entanglement entropies by default will grow actually according to a volume law of the subsystem, which means in our case the volume is just the length. You would have by default to expect the factor L. But that doesn't appear here. So that what makes it this is what makes it an area law, and area law should really be sort of a surface area law. And the surface of an interval is just 2 points, and C prime is proportional to 2. So I apologize for that, but that's really all there is behind it. So I already, of these remarks, explained the first one about the area law, that by default you could have a volume law, but we don't, so the entanglement entropy does not grow with the subsystem. the size of the subsystem in this one-dimensional subsystem. So, and we make an attempt at a physical interpretation of this. So, and here I really want to stress again all eigenstates, that we have a result for all eigenstates satisfied as uniform area law. And according to language which seems to slowly become standard in the physics literature, that would then mean that Hn is in the fully many-body localized phase. This is something where there is certainly not something like a many-body mobility edge or something. And maybe you want to think of this as the fact that we're in a one-dimensional system. And it was, I started from just a spin chain and not a higher dimensional spin system. But that's actually not quite true. I should use my chances. For spin chains not as trivial as the XY chain, there is actually a good deal of numerical evidence in physics papers that there is a one-dimensional transition, so that you need sufficiently large disorder to get into the fully localized phase. So it's a new situation, not like for the one-particle systems, which we all know to be localized at arbitrarily small disorder. But here in the XY chain, you have no transition, so you immediately get into the fully many-body localized phase. So here for this language, this comes mostly out of papers of David Hughes and co-authors, who has by now, I think starting in around 2006, about a dozen papers on this topic. There's a very nice paper also by Bauer and Noyak, two Microsoft people, from 2013, which I think they make an attempt of explaining also the Fock space localization picture in a way which might be slightly more accessible to mathematicians than, say, the original Basco, Alaina, Altschule paper. So now I can oppose this here or compare this with other results which were known about area laws in people who just study spin systems as their main profession. So Hastings proved a famous result in 2007, namely an area law for the ground state entanglement of general one-dimensional but gapped spin systems. As long as you assume, makes us write down a very general system of interacting spins with just relatively weak assumptions, maybe finite interaction lengths and some bounds on the constants. But you assume, where did I get? You assume that the ground state gap does not shrink to zero as the volume goes to infinity. So then he proved an area law for the ground state in such systems. But again, our result doesn't need a gap, and even more importantly, it applies to all eigenstates, not just the ground state. Also, closer to our result and actually very useful for our proofs was work by Pasto and Slavin from just last year, which Sasha Sobolev mentioned and which Leonid Pasto also mentioned when he was here in May. He actually proved an area law for the expectation of the ground state entanglement in disordered quasi-free fermion systems. And that is basically what we get after the Jordan-Wigner transform. So then we can actually make use of this result, but again, Pasto Slavin only did it for the ground state, and we had to do some extra work for general eigenstates. So I think instead of bothering you with too many of the proofs, I'll try to show you the last result if I have 4 more minutes, 4 or 5 minutes, on dynamical entanglement. So I need to have 1 minute to show you my concluding slide, so that is important. But, so you have to give me a 1 minute warning to stop with that. So here, maybe briefly, what do I mean by dynamic entanglement? So let me again split my interval into 2 halves, and now for simplicity just left and right end. And let me start. Now I want to look at the time-dependent Schrödinger equation and its solutions. So I need an initial state. I want my initial state to be a product state of a state on lambda A and a state on lambda B. So that is initially unentangled, because a product of 2 pure states is still a pure state. So I have an unentangled state in the bipartite decomposition, meaning at time 0 I have no entanglement with respect to this decomposition. Now I do the full spin chain Heisenberg dynamics using this originally unentangled product state. So, and the Hn is a full chain which has an interaction between L and L plus 1. So this will make things leak out and in, back and forth. So this will immediately get entangled, will become non-zero, and now the question is, if my whole spin chain is disordered, can I control the growth in T? It will be non-zero, but can I make it not grow too fast in T, and in particular also can I still have these uniform bounds in the size of the system and the subsystem? And indeed we have a result like that. Of course you have to talk about what do I choose for my phi A and for my phi B. And that is the most natural thing you could come up with. Let me, for phi A, choose an eigenstate of the left part of the spin system. So this is just the XY chain summing from 1 to L. In this case, R is now 1, with no interaction between L and L plus 1, particularly here. So basically I take the big spin chain and just cut off 2 interactions between the left and the right end. So then I get a spin chain on the interval 1L, and I get another spin chain on the interval L plus 1N. And I take an eigenstate of HA and an eigenstate of HB, and choose this product state as my initial state, but then do the full time evolution of for the interacting spin chain, and watch how the entanglement grows. And again we have a result if actually I didn't write that down properly. I need actually 3 assumptions. I need that all 3 one-particle Hamiltonians have eigencorrelated localization. I need it for Mn, which is the full, corresponds to the full chain, and I also need to assume it for the 2 subchains. So actually that's incomplete. I should have added these 2 conditions. Of course we know that both correspond to Anderson models, and so we know that again. Then I again get, so I get a uniform dynamical area law from that. So I can actually say that I can take time as large as I want, and I can also take N and L as large as I want, and that there is still a uniform constant. I should have said here there exists a C prime in the previous line, such that this holds completely uniform in N and L. So this is dynamical entanglement. This is actually directly inspired from some numerics we saw in a physics paper, but that physics paper then also gives the same numerics for the XXC chain. So that means you introduce another true interaction term, and then they actually start seeing this transition. Then they need sufficiently large disorder because they get it before they get a dynamical area. Now, if for small disorder they get this logarithmic correction, this log L correction, which we actually saw in Sasha Sobolev's talk for continuous fermion systems. So I'll skip over the proofs because maybe I already indicated, because I'm out of time mostly, but I indicate this is pretty close to some of the techniques Sasha has been using. It's a discrete version of much of this. We also learned quite a bit from Pastor Slavin from their 2014 paper. So, brief summary. To put things in perspective and to make sure that I'm not claiming more than what I can. So the random XY chain and also the harmonic oscillator systems, which I didn't get to, can serve as toy models to illustrate the physical characteristics of the fully MBL regime. And it demonstrated that specifically for the random XY chain. In the proofs we just get lucky because we can reduce these toy models to an effective one-particle system. It is ordered one-particle system where we already know things. So if you know this is, if you want, this is also known as cheating, what we're doing. So we're claiming that we have a many-body system and reduce it to a one-body system. I think there is a bit more to it, and the proofs also have a little bit more to it because it's not immediate. These one-bodies, you see, you reduce to free fermion systems as a first step, and free fermion systems are not really non-interacting systems because the fermion creation and annihilation operators do not commute, they anti-commute. And sort of the Pauli relations and exclusion principle introduces some kind of virtual correlations between them. So this is why there is still some work. But the physicists would still say in most of their papers the XY chain is a non-interacting many-body system. To some extent they're right. And if you go now to something like more general spin chains, then life gets much harder. And that is still the big open challenge, and I think so the only person so far who has seriously tried to get to this is John, is develop methods which can demonstrate the many-body localization for truly interacting systems such as, say, the Heisenberg model plus a random field. Or, okay, if you're really daring an electron gas where you have to go back to electrons as your single particles, so, but that will be even harder than that. So I don't know. We worked for 30 plus years on one particle localization. I'm not sure how long that program takes. So, but there is, I think, a start has been made, but I think there is much more to be done. Thank you.
So Gunter, do you think one could sort of, in terms of your picture, have this following maybe more general philosophy? So, as I understand your model, you have these spins that are trivially localized because it's a finite Hilbert space, and you place them somewhere and you let them interact, and then you prove localization of a spin base in terms of group velocity. Now, if we start with an Anderson model that is localized, we could think of, okay, we can label maybe the states on where they live, and then fill the space up with electrons, turn on some interaction, and somehow effectively connect this to a graph on what this interaction does, and then also have some kind of group wave through that graph, and then prove localization for that group.
You have read the physics.
And that would sort of mean.
So you're talking about Fock space localization, see, because the graph would be over the Fock space. So if anybody can say something about the mathematical answer to your question, I think it's John. But I think this is clearly the picture which you see from the papers like Basco, Alaina, Altschuler, so, which one wants to get to, and which Hughes is promoting. The answer is yes, this is what one should do, but I'm personally far from being able to at the moment.
When you had the last result, we basically took two independent Anderson models and disjoint boxes and intention. There's no interaction.
Yeah, but they get entangled in the many-body, on the many-body level. Yeah, it's not just adding an extra hopping term between two Anderson models.
You don't have the term, the link between the two. Okay. More questions?
In tandem production format that you have, it's like in Pascal's line, you can reduce it to one particle expression that comes projections.
Yeah, I didn't. Yeah. So I jumped over my 3 slides with a few ideas of the proofs. So Jordan Wigner is the first step, so that reduces it to Mn. I showed you that. And then the other big trick is that in these fermion systems, all eigenstates are fully characterized by the correlation matrices. And the correlation matrices are just 2n by 2n. These are just the expectations of arbitrary quadratic terms in these creation and annihilation operators. So you get done by 2n to 2n. And then it turns out that these correlation matrices just become eigenprojections of the effective Hamiltonian. So, and then you can stick this into the Pastur-Slavin proof, which uses this key formula, which reduces the entanglement of a state on the many-body space to an entanglement to a von Neumann entropy on the many-body space to a von Neumann entropy of this correlation matrix, which is now just in the one-body space. So and then you just stick in what we know about Anderson localization, and Pastur-Slavin has more or less the calculation.
Did your last theorem be true for arbitrary product states? I mean, you just did the ends, right?
Yeah, we actually have a version of that where you can split the whole chain into finitely many subchains. And no, we can do both. We can actually do a product state of, we can do this picture where one state is here and the other state is for this system, but that's a bit weird because they're actually not connected. And we can even do something where we split n into a fixed finite number of subchains and take a product of finitely many, not just 2, and then define entanglement with any one of the subintervals and get these bounds. Can play with that. Yes.
I was a little puzzled by you declined to interpret the XY model as something where you could see transport even though it does have like a spatial dimension, and you just interpret that as like particle dimension or something. I don't. Why do you?
No. I personally would not decline. I would. So you say I declined that.
You stated that it doesn't say anything about transport. The model. There's no transport in that model.
Yeah, that was the first theorem I showed. So no transport in a group.
No, but I mean,
In
I
a
don't mean
group
that there is no transport, but that the concept of transport is meaningless. It's essentially what you said, right?
No, I hope I didn't say that. I certainly did, and I certainly didn't mean it. Yeah, I think maybe that is what happened. So, I said particle transport in the configuration space of the particle for a single spin. I call that meaningless because a spin can only be up and down. Yeah, so this part where I want to make the difference between the vertical axis and the horizontal axis of my picture. So that in a many-body system, I wanted to say many-body transport is group transport. That should basically be in the horizontal direction, and by looking at a spin system as a toy model, you're sort of forced to focus on the horizontal direction because nothing interesting happens in the vertical one. That's all I attempted.
You were saying that the I index, spin index, was like a Fock space index rather than a spatial index. That's essentially what you said.
Yes. Okay. Yeah.
Right. But it's still okay. But you'll allow that you can talk about transport in the X one.
Sure, that may be a matter of how one uses terminology, but I hope I made it clear now what I mean. So maybe the terminology could be meant differently. But yeah, if you think as Fock space of the many-body configuration space, then all of this becomes a more classical, traditional form of transport again, just over the graph of this much bigger space. So maybe we can agree on that.
I have a question, just out of sheer ignorance of the thing. In the very beginning, you said that the accepted manifestation of such localization is closeness to product state. And I don't quite see why it should be like that.
It's the next
Why?
Next slide.
Yeah, well, I was careful here. I said rough, you know. So this was a rough thing, but so just so now try to make an analogy with the Anderson model. So in the Anderson model, say at least at large disorder, so we think of localization as, say, the potential wins. The potential, if I have the potential alone with a large coupling, then this is clearly localized because it's diagonal. All the eigenstates are deltas. And so what Anderson localization means in this sense, if I switch on the hopping, which at least in the large disorder regime is much smaller in magnitude than the potential, then this doesn't change so much. Okay, the eigenfunctions are not deltas anymore. The eigenfunctions are exponentially decayed, but close to delta functions. And now, what I say here, the eigenfunctions, the eigenstates of a many-body system being close to product states is an attempt at a many-body analog of exactly that. So if that means in my example with the XY chain, yeah, that would just be the magnetic field, what I'm looking at here. So maybe with very strong coupling. And as long as I don't have the hopping, the many-body hopping, the eigenstates would just be product states. That's just simple properties of these simple operators on tensor products. And now if I get lucky and have a similar phenomenon as in one-dimensional Anderson localization, or one-particle Anderson localization, I can hope again that after switching on the interaction, at least on a qualitative level, the eigenstates stay somewhat similar to the eigenstates of the non-interacting system. But these are now product states. It's not delta functions, it's product states.
So let's thank the speaker. We will start at 11:30.